On week 3, we manipulated with the polar map we did in slightly different way, actually. I'll try to bring this in your memory. So back then we said, let's just take the inverse polar map, and I gave these names to this inverse map. Back then I didn't really stress much why we do have such an inverse map. Now we know we do have it, because when you compute the Jacobian for the forward map, when you compute the Jacobian for the forward map, which is the formula for the Jacobian, that's the same expression for the Jacobians we just saw on the main set of slides. Or we can actually express every component in the Jacobian in terms of x and y. That's how it is. Cos theta is just x by r. Sine theta is y by r. And these two, simply negative y, negative x. That's just alternative expression for the same Jacobian in terms of x and y and r rather than theta. If you compute this Jacobian, and that's another computation of the same Jacobian, it is r, and it is non-zero. And it is non-zero. Every time except the origin. And that's why we do have such an inverse. Now, when we show that such an inverse exists, on week 3, we saw another way to compute the partial derivatives of the inverse map, and by implication, the Jacobian of the inverse map, right? So this object, the Jacobian of the inverse map, now, but there was a third way to compute that. First one we just did today by inverting this matrix. It's via this is by the inverse function theorem. Second one, there was again on the slide today when we just we found the expressions for these functions, explicit expressions, and we just differentiated them. It wasn't easy. They only worked in the first quadrant, but still it was sort of doable. The third one, as a matter of fact, should be the first one because we done it on week 3. I'm not going to bring this up, but I just bring the computations we come up back then. We did it twice. We did it by hand and with Maple. That's the computations we come up back then for the partial derivatives of my inverse polar map. That's what we had back then. By earlier computation, was a slide called Polar Substitution 1, week 3. Why did I bring this up? I brought this up for one reason. I want to double check this theorem of the inverse function once again. And now I want to double check it in the full generality for the polar map. I want to convince you that now if I multiply this matrix by this matrix, having this analytical formula for every component of this matrix, both Jacobian of the P map and Jacobian of the P inverse map, polar inverse map, if I multiply these components analytically, I will see this relation that the one is the inverse matrix to the other. So if you multiply them, you will come up with the identity of size 2. Here's the verification. So if I compute this product, right, I have to take the first row here, dot product with the first column here. Here it is. XR times RX, X theta times theta X. If I sub in my analytical expressions, and I prefer to sub them in the form X and R, that's a substitution. And that is 1. XR for X on R by XR. Another X on R for RX from here. X theta from here, X theta is here, negative Y. And theta X from here, negative YR squared. If you compare this with the direct computations, when you had the direct formula for the inverse, there will be the same formula there. But the good thing is we come up with this without any help from knowing the formula for the inverse. And that verifies the first part, right? The dot product of the first row, first column is 1. This is a dot product of the first row and the second column. XR, X theta, it's the first row from here. It is X by R and negative Y here. X by R and negative Y. And RY and theta Y, it's from here. One value came from here and the other from here. It's 0. another two lines, so to verify this identity. This is a product of second row here with the first column here. Y by R, it's for this YR, yes, right here. X by R, this is the, it is RY. Yeah, that's right. No, Rx, sorry. From here. X is this component, and negative Y by R square is this component. And it is 0. Very simple arithmetic. And the final line, it's the dot product of the last row and the last column. And that should be 1. YR. It's YR is here. RY from here. And here we got X and theta by Y. That's right. Every time, of course, here, I mean, when you come up with this 1, we use the fact that X squared plus Y squared equal R squared.